Maybe we're ready to start. So welcome, everyone. I would like to thank you for being here, for joining this seminar series. So I'm Matteo. I'm organizing this seminar series, Combinatorics, Physics, and Probability at Harvard CMSA, together with Michael Simkin. And seminars will be every Tuesday from 9:30 to 10:30 a.m. in the US Eastern Time. These talks will be recorded and will soon be available online on CMSA website. So as mentioned in the posters and in the previous sections, the purpose of these seminars is to explore two main threads. The first is the interaction between combinatorics and physics, and the second will be about the interaction between combinatorics and probability, which will be more Michael's domain. And you will hear more next week. I'm happy to continue exploring the combinatorics and physics today with this talk given by Pavel Galashin from UCLA in the departments of mathematics on Ising models, total positivity, and criticality. We will leave some times for questions at the end, but feel free to ask brief questions during the talk, either on the chat or unmuting yourself. So please, Pasha, feel free to start.
All right, thanks. Yeah, thanks for the invitation and thanks for coming. So yeah, it's going to be about the Ising model and total positivity and criticality. And yeah, I was actually looking at the name of the seminar and I found that it kind of matches perfectly with the title. So maybe, I don't know, total positivity is combinatorics and the Ising model is probability and criticality is physics, or maybe they are switched. I'm not actually sure, but yeah, together they are kind of. And then I was looking at the list of co-authors and actually you can match them too. I mean, kind of Pasha is combinatorics and then Steven is maybe probability. And so, yeah, actually, I'm not sure about these two, but anyways, there is a partial bijection between all these objects. And actually, yeah, I guess what I'm saying is that the talk is going to involve combinatorics and physics and probability. So they're kind of all going to be mushed together in this talk. And so I'm going to start with total positivity and some of its topological aspects as a sort of somehow they're going to later lead to the Ising model statements. But for now, so let me focus on the total positivity. And the main object here is the Grassmannian and the totally non-negative Grassmannian, which I'm going to abbreviate as the TNN Grassmannian. So first of all, the usual Grassmannian is the set of all linear k-dimensional subspaces of R to the n. And so you can think about this space in terms of matrices. Right? If you take a subspace and you choose a basis, then it's going to be a full rank k by n matrix. So you can, if you choose a different basis, you're going to get different matrix, and the two are going to be related by row operations. So I'm going to usually work with this definition here. And so here is an example. Here's a 2x4 matrix, and it's full rank. So if I take the row span, the rows are going to give me a basis of a two-dimensional plane inside the four-dimensional space. And of course, if I apply some row operations, the row span is not going to change. So I can't really directly talk about the entries of my matrix. But I can instead talk about the Plücker coordinates of my matrix, which, so by definition, what you do is you choose a set of k columns. Maybe you choose these two columns, and then you take the determinant. So that's going to be the corresponding Plücker coordinates. Just these are the maximal minors of my matrix. And these are basically invariant under row operations, except that they are, well, if you multiply some row by 5, then all Plücker coordinates are going to get multiplied by 5. So they give me projective coordinates on the Grassmannian. And for this matrix here, you can compute all Plücker coordinates. Here is like for instance, delta 2, 4 is the determinant of this 2x2 submatrix. And yeah, so you get n choose k numbers for every matrix. And actually notice that here, the matrix looks sort of random, but actually the Plücker coordinates are kind of special because they are all non-negative, or rather they all have the same sign, right? So that's the key definition of the TNN Grassmannian, which was introduced by Postnikov in 2006. So the TNN Grassmannian is the subset of the usual Grassmannian, where all Plücker coordinates have the same sign. For example, this matrix here belongs to the TNN Grassmannian 2,4. And yeah, so in particular, this is a nice compact subset of the Grassmannian, and you can try to study the topology of the space. And this was sort of initiated by Postnikov, who showed that if you take, so this space is subdivided into cells. Namely, all the minors are non-negative, so you can look at cells where you kind of fix a bunch of minors to be, and require them to be strictly positive and require the rest to be equal to 0. And so you get a stratification of the space, and then Postnikov showed that each of these strata is an open ball. So in particular, there is one open dense cell where all minors are strictly positive. Like for this matrix here, right? All minors are strictly positive. So this cell is like the interior of the Grassmannian. It's called the totally positive Grassmannian. So it's also an open ball. And then he conjectured that if you take the closure of any such cell, so you make some minors 0 and the rest non-negative, what you get is going to be homeomorphic to a closed ball. And there has been a lot of progress on this conjecture, and actually the progress started even before, way before this 2006 conjecture. So the first result is due to Lusztig in '98, well, where he introduced a totally non-negative part of an arbitrary partial flag variety, and many years later it was shown that the TNN Grassmannian is a special case of those. So Lusztig showed for his partial flag varieties that the totally negative parts are contractible. And later, Lauren Williams showed that basically, she showed that there are no combinatorial obstructions to this conjecture being true. So you can study the combinatorics of how different which cells are in the boundary of which other cells, and sort of there is a notion of a shellable poset, which implies that combinatorially it looks like it comes from a ball, but actually you still have to show that the actual topological space is homeomorphic to a ball. And then later, Postnikov, Spire, and Williams showed that this is a CW complex. And then later, Rich and Williams showed that this conjecture is true up to homotopy. So each closed cell may or may not be homeomorphic to a closed ball, but at least is contractible. So no homological obstructions. Yeah, and actually, so in our paper with Stephen and Thomas, what we did is, first of all, in 2017, we showed a special case of this conjecture where so you remember there is one open dense boundary cell, and if you take the closure, you get the whole space. So this conjecture includes that the whole TNN Grassmannian is a closed ball. And yeah, we were able to prove this in 2017, and then a couple of years later, we were actually able to finish the whole conjecture. So each cell, if you take the closure like this, then you get a closed ball. And yeah, so these are some topological results. And actually, the second one is much harder to prove. It relies on affine flag varieties and the generalized Poincare conjecture, you know, the Perelman and Smale and Friedman results. So there is some heavy machinery going into this theorem. But actually, this theorem is not going to be relevant to this talk. But the first theorem, and the easy part that the whole space is a ball, actually the proof is going to be directly relevant to the Ising model. So let me try to outline the proof of this result here. So here's the theorem again. And so how would you prove such a theorem? Well, let me try to draw the TNN Grassmannian. Maybe it looks sort of like this. It's not a polytope, but it sort of looks like a curvilinear polytope. And if it were a polytope, what you would do is you would pick some point, x0 in the interior, and then you would try to subdivide the whole space into trajectories. Maybe for polytopes, this would be straight lines. And then you would draw a tiny ball around x0, and you would use your trajectories to contract, to sort of find a homeomorphism between the whole space and the and you're a closed ball. Yeah. But of course, I mean, this is a simple idea, but for the TNN Grassmannian, the hard part is the details. What is the point and what are the trajectories? It's sort of not exactly clear. And so what it turns out, the construction that actually works looks like this. There's a certain cyclic shift map. The Grassmannian has, the TNN Grassmannian has the cyclic symmetry. And this special point is actually, the point that works is it turns out that there's a unique point that's cyclically symmetric inside the TNN Grassmannian. So yeah, that's basically the proof idea, right? So there's a certain vector field which gives you these trajectories, and they all float together towards this unique cyclically symmetric point. And let me explain this further. So first of all, what is the cyclic symmetry on the Grassmannian? Well, it's what you do is, I guess it's slightly weird because you look at the columns, and basically, so every element of the Grassmannian is the row span of a k by n matrix. And if you look at the columns, then each of them is going to be some vector in c to the k. So what you can do is you can take the last column and you can move it to the first place. But that is going to mess up the signs of the minors. Some minors are going to become negative. But if you twist the sign by -1 to the k minus 1, then it turns out that you preserve the total positivity condition. So this cyclic shift map preserves the TNN Grassmannian. And in particular, because I mean, it's a continuous map, and I already told you that this space is a ball, so this map has to have a fixed point. Even though if you look at the level of matrices, right, if your matrix is a full rank matrix, then there's no matrix that actually, as a matrix, would be invariant under this map, because all the columns would have to be proportional to each other. So at the level of matrices, there is no fixed points, but at the level of the Grassmannian, there is a unique fixed point. And for example, let's say I take the case of the Grassmannian 2, 4, and then I claim that the unique, this special point x0 is the row span of this 2 by 4 matrix here. So let's see, if I take this 2 by 4 matrix and I take the last column and I move it to the first place and I change the sign because of this thing here, I get another 2 by 4 matrix. And these, as matrices, these are not the same. But I claim that when I take the row span, I'm going to get the same element of the Grassmannian. And there are two ways to see that this is true. First of all, I can look at the columns and I can plot them in the plane. So for the matrix on the left, the columns are going to, the first column is this vector here, and then the 4 columns are shown here. And then, so I take the last column and I change the sign and I move it to the first place, so I get a different picture here. But my row operations would correspond to kind of global linear transformations of the plane. So in particular, there is a rotation by 45 degrees, which would take the configuration on the left into the configuration on the right. And that's why it's cyclically symmetric. So that's one kind of pictorial way to see this. Another way to see this is to just compute the Plücker coordinates of either of the two matrices. The Plücker coordinates are the same, and they are positive and cyclically symmetric. So the conclusion is that this point is the unique cyclically symmetric point of the TNN Grassmannian 2, 4. Now, that's basically it for the total positivity part. Now I'm going to completely switch gears. Let me know if there's any questions. But what I'm going to do is I'm going to switch gears and talk about the Ising model for a while, and then I'm going to connect them together. So the Ising model is a certain, well, it lives on the graph. You start with a planar graph in a disk. It's important that you have some boundary vertices, and then you also have the edge weights. And the edge weights are assumed to be between 0 and 1. That's called the ferromagnetic Ising model. Oh, there is a question. Maybe good to mention Stephen Karp first found the cyclical. Yeah, right. Okay, so Stephen, right? That's there is a paper by Stephen which finds the cyclic symmetric point for all k and n using eigenvectors of this cyclic shift. Yeah, thanks, Lauren. Yeah, so the Ising model lives on a graph, and the ferromagnetic Ising model asks that all these edge weights are strictly between 0 and 1. And so what is the Ising model itself? It's a certain probability measure on the space of spin configurations. And here is a precise definition. So first of all, what is a spin configuration? A spin configuration is just an assignment of plus and minus ones to the vertices of my graph. So maybe I can try to draw one. So just put a plus or a minus on any vertex of my graph, maybe something like this, minus, plus. That is an example of a spin configuration. And then each spin configuration has a probability. The probability of a spin configuration is, what I do is I look at all edges where the spins at the endpoints are not the same. So maybe here's an edge where the spins at the endpoints are different. So and then I multiply the edge weights of all those edges. So here the probability is going to be x2, x3, and x5. Yeah. And then I divide by z, where z is the partition function, which just by definition, you take the sum of all these numerators to make the total probability to be equal to 1. Yeah, so that's the Ising model. And I'm going to be interested in certain, so you should think of the spins as actual, maybe each vertex is an electron, so it has a plus or minus spin. And this whole thing is like a little metal plate. So what I'm going to try to do is I'm going to try to measure things at the boundary. So I'm going to look at my boundary measurements, which are correlation. Yeah, I'm going to look at correlations between the corresponding spins for two boundary vertices. So here is a definition of the boundary correlation. Right? You fix two vertices bi and bj, and then by definition, the correlation is the probability that the two spins are the same minus the probability that the two spins are different. So it's some real number between -1 and 1. And actually, so if you look at this formula here, right, the model is ferromagnetic, which means that the more spins, whenever I see an edge with two spins are different, I have to pay the price. Right? I have to multiply by a number that's between 0 and 1. So the more spins are misaligned, the lower is going to be my probability. And in particular, it's sort of natural to conjecture that these correlations should generally be positive or non-negative at least. And that actually turns out it's pretty tricky to prove, but it is true. For not necessarily planar graphs, it was shown a long time ago by Griffiths in 1967. Yeah, just all correlations are non-negative. And moreover, so the year after that, Kelly and Sherman showed that the correlations satisfy some other nice inequalities. So here is an example of a triangle inequality, and they found some even more general inequalities. And they asked the question. The question is, can you find all possible inequalities? So maybe, strictly speaking, maybe I give you all pairwise correlations between any two boundary vertices. Can you check that this collection of correlations comes from some planar ferromagnetic Ising model? And another question, which is, so I'm gonna answer the first question, and the second question I'm also gonna answer, which is very natural from this perspective, is, let's say you know all pairwise correlations. Can you recover what's inside? For instance, if you know the graph, can you recover the edge weights? Or maybe you don't know the graph, and then you recover, to what extent can you recover the graph and the edge weights, like the inverse boundary problem. And so both of these are going to follow naturally from the approach I'm going to describe. And yeah, so let me copy the definition of the Ising model and of correlations to the next slide. Yeah, so let me state the problem precisely. What I'd like to do is I'd like to study the boundary correlation matrix. So let's say I have n boundary vertices. Then I form an n by n matrix where each entry Mij is just the correlation between the corresponding two boundary vertices, Bi and Bj. Now, I'd like to study the space of all such boundary correlation matrices. So I take all, so I'm only looking at n by n matrices. So I fix n, and then I look at all possible graphs with n boundary vertices, and then I look at all possible edge weights. So I get infinitely many matrices, and that's going to be my space x of n. And actually, as you're going to see very shortly, this space is sort of weird. It's kind of neither open nor closed. It's, for some technical reasons, it's actually much more natural to study the closure of the space. Right, so I just take the closure literally in the space of matrices. Yeah. So for example, let's say I take an example where n is equal to 2. So I have two boundary vertices and then some number of vertices in the interior. Doesn't really matter. Let's say I just have a single edge between these two vertices. Then I can compute the boundary correlation matrix. The boundary correlation matrix is going to look like this. So it's a 2 by 2 matrix, and it has ones on the diagonals because the correlation between I and I is equal to 1. And it's also symmetric. And the object sigma I sigma j is equal to sigma j sigma I. So there is only one interesting entry in this matrix. And this entry is, you can compute it from the definition explicitly. It doesn't really matter what it is, but here is the actual answer, 1 minus x or 1 plus x. And what matters is that as x goes between 0 and 1, this value, well, this correlation takes almost all possible values. Right? It goes from 0 to 1 as well. And these are, remember, each correlation is weakly between 0 and 1, but this value takes all values strictly between 0 and 1. So the conclusion is that this space x sub 2 it consists of all matrices where m is between 0 and 1, where 0 is included, but 1 is not included. Why is 0 included? Because you can remove the edge, so then the correlation is going to be 0, but you can never get to 1. To get to 1, you would have to contract these two edges. You can never force the two spins to be exactly the same. Yeah, so, and if you contract the edge, that's sort of not allowed, because then you have to have two boundary vertices, but they're going to kind of glue together. So that's the kind of technical problem with this space here. But when you take the closure, it all works out. So when you take the closure, the only new thing you get is you are allowed to contract edges even when they connect two boundary vertices. And in particular, in this case, I'm going to get the whole line segment, closed line segment from 0 to 1. And notice that this space is homomorphic to a closed one-dimensional ball. Yeah. So let me know if there's any questions. Now, what I'm going to try to do now is I'm going to try to go back to the total positivity story and relate them together. So here's the reminder on the TNN Grassmannian. And I'm going to consider, right, it's the space of the subset of the Grassmannian where all Polygon coordinates are negative. And I'm going to consider a subset of this set. So it's a subset which actually was introduced by physicists, Huang and Wen, in 2013. So it's called the TNN orthogonal Grassmannian. And here's the definition. So let's see. You take the Grassmannian of n, 2n. Let me try to draw I'm looking at n by 2n matrices. N to n. And then I'm looking at, so first of all, each minors have to be non-negative. It's a subset of the TNN Grassmannian. And second of all, there's this orthogonal condition. Each minor has to be equal to the complementary minor. So let's say I choose some set I of columns, and then delta I should be equal to the minor spanned by the complementary n columns for any I. So each Polygon coordinate is equal to the complementary Polygon coordinate. That's the condition. And there is as you know, the orthogonal Grassmannian corresponds to some symmetric bilinear form. And there is a way to choose a bilinear form which would give you this condition here. So that's why it's called orthogonal Grassmannian. So yeah, so the goal is to relate this space to the Ising model. Here are the two spaces that I would like to relate. The TNN orthogonal Grassmannian on the one side, and the space of n by n ferromagnetic planar Ising boundary correlation matrices. So how do I relate the two together? And the answer is, well, let's say I take an n by n matrix here. So the answer is going to be given by a certain map, which we call the Dublin map. Which what it's gonna do is gonna take each matrix here, and it's gonna produce so from an n by n matrix, it's gonna give me an n by 2n matrix. And the way it's gonna work is, so here's an example. You take your n by n matrix, which is symmetric and has ones on the diagonal, and then it's a Dublin map. You just double every column. So maybe you take the first column and you make 2 copies of the first column. And then you do the same for the second column and the third one and the fourth one. Yeah, and then there's also some signs. So you insert some minus signs in an alternating way, which I'm not going to explain, but there's a very simple rule for the minus signs in this matrix. And then I take the row span. So at this last step, taking the row span, it looks like I'm losing some information. When I take the row span, I can't really recover the entries right away. But the claim is still that this map is injective. Surprisingly, well, actually not surprisingly, there is a pretty simple linear algebraic exercise where you can, if you only are given the row span of this matrix, there's actually you invert some matrix, etc. You can actually recover all of these correlations and this whole matrix just by linear algebra from this row span here. So this is a completely constructive bijection, well, injection, which has an inverse that's also easy to write down. So it's an injective map which lands inside the Grassmannian. So a question is, what is the image? What is the image of this map? And let's try an example again. So here's an example where n equals to 2. And remember my space x sub 2 bar consists of matrices of this sort. So now what do? I need to take each of these matrices, and then I need to apply the doubling map. So I double every column. Yeah, basically I get this 2 by 4 matrix, which is a 2 by 4 submatrix of this matrix here. And then I take the row span. So I have to look at the Plücker coordinates. So here are the Plücker coordinates on the right, and like for instance, delta 1, 2 is 2m. That's the determinant of this matrix here. And what you see is that, first of all, each Plücker coordinate is equal to the complementary Plücker coordinate. So that's kind of nice. And second of all, if you ask that all of these Plücker coordinates are non-negative, then let's see. So first of all, m has to be non-negative, and then also m has to be at most 1. So these inequalities that the minors are non-negative precisely cut out the space x sub 2 bar by inequalities. And that's that answers the question from the first slide, where like, how do you describe the Ising model by inequalities? Well, each minor is a polynomial function in the correlations, and then if you ask that all of these are non-negative, then at least for n equals to 2, you precisely recover the space x2 bar. Now, so what happens for general higher values of n? And the answer is that for higher n, the result is precisely the same. So here's a theorem which we proved with Pylyavskyy a few years ago, is that this Dublin map is actually a homeomorphism whose image is the TNN orthogonal Grassmannian. So not only it's injective into the whole Grassmannian, but if the image turns out to be actually the TNN orthogonal Grassmannian. So you can go back and forth between these two spaces. There's bijections in each direction. And we also proved, using basically the same idea with the cyclic shift, that both of these spaces are closed balls. And there was one more thing we proved a whole bunch of properties where you take some natural object for the Ising model, and then you apply the Dublin map, and you recover some other natural object on the Grassmannian side. So in particular, we showed that the there's a certain operation which is called the Kramer's linear duality for the Ising model. It gets translated into the cyclic shift on the Grassmannian. The same cyclic shift that I mentioned at the beginning with the topological part. And so why, I'm not going to explain this duality, but it was invented originally to compute the critical temperature of the Ising model. And so we ended our paper with a speculation that there should be some way to kind of take this cyclic shift and the cyclic symmetric point and somehow prove some statements about the critical Ising model. So that's what I'm gonna try to explain next. Please let me know if there's any questions. All right. So the critical Ising model is basically the reason why the Ising model is important. And let me try to go back 100 years ago and try to actually motivate the critical Ising model from the historical perspective. So the origin of the Ising model is that it was invented by Lenz. And Lenz, so he had a PhD student, Ising, and he suggested this model to Ising. And Ising started to study this model and wrote a thesis on the Ising model. And in that thesis, he concluded that this is not a good model for magnetism. And so what does it have to do with magnetism, first of all? And here's an experiment. So what you can do is you can, basically you take a piece of metal. Maybe you can you can buy some piece of nickel from Amazon, and then you can take some strong magnet. So maybe some neodymium magnet. And then, so your nickel is going to be attracted to the magnet with some force. And then you take like a kitchen lighter, and then you actually heat up your piece of metal. And what you're going to see is that the force, as the temperature increases, the force is going to change in some way. So the question that people have studied a while ago is what happens to the force as you heat up your piece of metal? And there could be many possible answers. It could decrease kind of smoothly, or maybe it could increase, or maybe it can have some special point where it's not even continuous, or maybe not, it's not differentiable or not continuous. Yeah, there's many possibilities. And as probably all of you know, the actual answer to this question is this plot right here. So there is a special point, a special temperature, which is called the Curie point of your metal. And for the nickel, it's actually pretty low temperature, so you can achieve it with the kitchen lighter. And so it's the Curie point, which is a special, so that's where the phase transition happens. Okay? There is a sharp change of properties as you go even slightly above the critical temperature. And you can see that it was discovered not too long ago before the Ising model was introduced. So people were kind of looking for a nice mathematical model for magnetism. And this nice model would have to have a phase transition. And in particular, what Ising showed, well, he showed correctly that if your graph is a path, like a one-dimensional lattice, then there is no phase transition. And so he concluded there should be no phase transition in higher dimensions. And that was actually wrong. So for a while, people didn't study the model, but actually at some point they discovered that there is actually a phase transition in 2 dimensions and above. So clearly this is the physical demonstration of the phase transition, but what is the mathematical interpretation of that? And here's the mathematical interpretation of phase transition in, let's say, 2 dimensions. What you do is, first of all, I gave you a very general definition of the Ising model. Usually people take a much more special definition where your graph is just a piece of the square lattice. So instead of an arbitrary graph in a disk, I take some graph like this. And then I also don't take arbitrary edge weights, but I take all of them to be just the same number, just the same x. And then as I vary x, I'm going to look at the properties of my Ising model on this graph. And it turns out that there is a phase transition. So the picture looks kind of like this. There is a single value of x, which is called the critical value. And if you go even slightly above the critical value, what you see is just white noise. If you go even slightly below the critical value, what you see is that your spins organize into large clusters where the spins are the same. So you see some long-range interactions between spins that are far away. And so naturally, what happens at the critical temperature is the sort of at this critical value, the model has the most interesting properties mathematically. You can study all sort of SLE curves and things like that. Yeah. So, but the point is that there's a single value. So, what is this value? It should be just some number between 0 and 1. And that value was computed by Kramers and Wannier. The same, I mentioned their duality, which corresponds to the cyclic shift. They were the first one to compute the critical value. And for the square lattice, is just given by square root of 2 minus 1, which is a number between 0 and 1. So that's good. Now, what about the other lattices? You can take, instead of the square lattice, maybe you can take the hexagonal lattice or the triangular lattice, and you get different values. Turns out that there's no canonical critical value. It depends on the lattice. And what is the pattern between these numbers? Looks kind of nice. So what is the pattern? And the pattern is that, first of all, you can write each of them as the tangent of a certain nice angle. And the angle has to do with the angles in the lattice in some sense. Yeah. But let me state this more precisely. So what I'm going to do is I'm going to try to draw, for every edge of my lattice, I'm going to try to draw a little rhombus around that edge, so that together these rhombi form a rhombus tiling of the whole plane. Like this. Yeah. So here is the picture that I'm going to get. The dashed edges are the rhombi, and the solid edges are the original lattice edges. Now, in terms of these rhombi, the rule for these tangents is very simple. Whenever you see a rhombus, like each edge is the diagonal of a single rhombus. So whenever you see such a rhombus, you just set the edge weight, the critical edge weight, to be the tangent of theta over 2, where twice theta is the angle that's opposite to the edge. So this explains all of these critical values for different lattices. But actually, it also gives us much more freedom, because now you can take an arbitrary rhombus tiling of the plane. You don't have to make sure it's periodic or regular in some sense. So you get much more general rhombic lattices this way. And so that was first done by Baxter in 1986. So he called it the critical Z-invariant Ising model. And what you do is, first of all, let's not even take some infinite tilings of the plane. Let's take a finite polygon. Just let's say R is a finite polygon which admits a rhombus tiling. So that's R. And then what you do is you choose a rhombus tiling. And then you convert it into a graph. So you color the vertices of your tiling in a bipartite way. And then you draw only the diagonals between all black vertices. So you get a graph. You get a planar graph in a disk with a whole bunch of boundary vertices. And that's going to be my graph G. And then for the edge weights, you want a weighted graph. So you choose the edge weights in exactly the same way as on the previous slide. Just use the critical value here. So you get a weighted graph, and then you can study the Ising model on that graph, and that's going to be called the critical Z-invariant Ising model. So why Z-invariant, first of all? It's called Z-invariant because of this. It has a special property, which is that if you look at the boundary correlations, well, or generally, the whole model is invariant under certain local moves, which are called flips. So what is a flip? You find 3 rhombi which together form a little hexagon, and then you replace them with the other 3 rhombi that form the same hexagon, and that's a flip of a rhombus tiling. And at the level of graph, it corresponds to a star triangle move. And these edge weights are chosen in such a way that whenever you apply a flip, the correlation between any two outside vertices is preserved under these transformations. So this is sort of like a trigonometric solution to the Young-Baxter equation, in a sense. So in particular, it is a result which is due to canyon, which is that any two rhombus tilings of a given polygon can be connected by a sequence of such flips. So in particular, the conclusion is that the correlations between boundary vertices, they do not depend on the choice of the tiling. Right? The correlation between B1 and B2 depends only on the shape of the region and not on the choice of the tiling. So in principle, the motivating question for the rest of this talk is going to be to try to give a formula for the boundary correlation matrix in terms of just the shape of the region. So I'm not allowed to choose a rhombus tiling in the interior. So, all right. And before I even give you a general formula for arbitrary regions, let me focus on the most symmetric special case. I'd like to consider the case where my region is a regular polygon. It has to admit a rhombus tiling, so it has to be a regular 2n-gon. So for example, here is a regular 2n-gon, which with the choice of some rhombus tiling, and then I can convert this rhombus tiling into a graph, right? A weighted graph using the procedure from the previous slide. So I'm going to get n boundary vertices and then some stuff in the interior. So when I measure these boundary correlations, they do not depend on anything. They do not depend on the choice of the tiling. They only depend on the value of n. So what is the formula for these boundary correlations? And here's the formula. So first of all, so you choose two vertices bi and bj, and then first of all, their correlation depends only on the distance between I and j, because the whole picture is cyclically symmetric. And the way it depends is, well, the actual formula is here. So d is the distance between I and j, and then what you do is you take the sine of pi over n and then 3 pi over n. Yeah, you just take odd multiples of pi over 2n. And then you alternate the signs, basically. So that's the formula. And it looks kind of long and complicated, but actually it's a pretty simple formula if you think about it. Compared to like going through all possible spins inside some rhombus tiling, this is pretty easy to compute. And let me play with this formula a little bit more. So first of all, here is the first few values of the formula. When d equals to 1, the value is given, it just has one term, or two terms. Here's when d is 2, and when d is 3. So you see that I'm getting just 1, 3, 5, 7. I'm just getting all these odd multiples of pi over 2n. And let me mention that, for example, each of these individual terms has a limit. So this, as n goes to infinity, this converges to like 4 over pi minus 1, and etc. So each of these has a limit. And actually, let me consider a slightly different limit. Let me consider a limit where, so here for all these examples, d was finite, but let me consider a limit where d goes to infinity, but it's still much smaller than n. So let's see what's going to happen. First of all, d is much smaller than n, so I can get rid of all the signs. The signs can be replaced by their arguments, and then after that I can cancel out the n's. So what I get is 4 over 2d minus 1 times pi minus 4 over 2d minus 3 times pi plus etc. minus plus 4 over 3 pi plus or minus 4 over pi minus plus 1. I get an infinite series like this. And here, so d goes to infinity, so I have some infinite alternating series. And this question is asking whether the series converges to 0 or not. And it looks kind of tricky. Why would it converge to 0? But the answer is actually that, first of all, let me rewrite this in a prettier way. So here's the same formula as I had before. So the claim is that it converges to 0. It converges to 0, and the reason is the Leibniz formula for pi. Namely, if you take the alternating sum of all inverses of odd integers, what you get is pi over 4. And so you take this formula, you multiply it by 4 over pi, and you get this formula here. So it's kind of nice that this formula for the Ising model includes the Leibniz formula for pi as a specialization. And using this Leibniz formula for pi, you can actually find all kinds of asymptotics of this formula. And in particular, you can, so here's one asymptotic result that I got. So first of all, here's the formula again. If you take the asymptotics and you rescale the limit properly, the statement you get is that if you have a limit of regular polygons which converge to a circle, then the scaling limit of the boundary correlations is what you would expect from conformal field theory. So there are some predictions from conformal field theory that the limit should be conformally invariant and universal in some sense. So for the circle, I proved that the result is actually what confirms the prediction of this conformal field theory. And I should mention that there has been a lot of results of this form. So notably, there is a paper by Chelkak and Smirnov, which deals with points in the interior of the region. And there is also a paper by Angler, which sort of extends to some regions, to the boundary of those regions. But somehow, none of the papers apply to the regular polygons approach in the circle. So there are some technical conditions here which are not satisfied in this situation. And so this somehow turns out to be a new result. And yeah, so now let me go back to arbitrary polygons, because I promised to give a formula for an arbitrary polygon. And yes, remember, here's my motivation. And I want to describe the boundary correlation matrix for an arbitrary polygon purely in terms of the shape of this polygon R. So first of all, what is the shape of a polygon? Let's say I have a polygon. So what I'm going to do is I'm going to label its boundary by vectors v1, v2, etc. Just some unit vectors in the plane. And then I'm going to, instead of using the vectors, I'm going to use their arguments. So let me denote by theta. My theta angles are going to be basically each twice theta is the argument of the corresponding v vector on the boundary. And so these theta angles basically describe the shape of my polygon. And my formula is going to be purely in terms of the theta angles. And the way the formula is going to work is I'm going to introduce a certain curve. Let's say I fix the thetas, then I'm going to have a curve which lives inside the 2 n-dimensional space. And so let me give you an example of how this curve looks like. Let's say if my region is convex, then the curve, so it has 2 n coordinates, right? And it depends on some parameter t. So each coordinate turns out to be given by just a product of signs. And there's n minus n different terms in each product, and they sort of increase j from 2 to 3 to 4, all the way up to 2n and to 1. And once it starts wrapping around, you get some plus or minus signs in front. But basically, yeah, these are the explicit coordinates of my curve. And that's when your polygon is convex. If it's not convex, then there's a similar formula. Each coordinate is still a product of n minus 1 terms, but then the actual terms are going to depend on the combinatorics of how non-convex is my polytope. So there, yeah, if you know about Grassmann necklaces, then this J has to do with Grassmann necklaces. Yeah, but anyways, I have a very explicit curve for each theta angles. And then the claim is that this curve is the formula. So here's the, I guess, the final result of the talk. It's a bit anticlimactic because it's just a bunch of symbols. But let me remind you what the symbols actually mean. So first of all, the doubling map here is, well, the map phi is a doubling map, right? It takes each matrix and doubles every column. So you get an element of the T and N orthogonal Grassmannian. That's the left-hand side. And the matrix M sub R is the boundary correlation matrix, which you get for a polygon, which, remember, it does not depend on the choice of the rhombus tiling. So that's the left-hand side of my equation. And the right-hand side is, I just take the linear span of all points on gamma. So gamma is a curve in R to the 2n, and it turns out to be degenerate. So it's not like the moment curve, which spans the whole space. It actually lies in some degenerate n-dimensional subspace of R to the 2n. And the claim is that, so if I take the linear span, I get an n-dimensional space inside the R to the 2n, which is an element of Grassmannian n comma 2n. So the claim is that these two are equal to each other. And let me finish with a few brief remarks. So first of all, this is a very constructive statement. You can find the inverse easily if you have a computer which knows how to invert matrices. Then you can actually compute the span explicitly, and then you can get the actual boundary correlations for any shape. It's very fast. You can take like 1,000 by 1,000 square grid and compute the correlations very quickly. And the second point is that there is a similar story which I skipped about the electrical resistor networks. And basically there is another embedding into the Lagrangian Grassmannian of n plus 1 comma 2n, which is due to Thomas Lamb. And the whole story generalizes to these electrical networks and more generally to the critical dimer model. Now, finally, another remark is that when R is a regular polygon, remember, in that case, I had a very simple formula. And the reason for that is that in this case, the span of my curve, basically both sides of this equation, are the unique cyclically symmetric point in the TNN Grassmannian. So in that case, you can actually invert the matrices explicitly and get the formula with the signs. So that's it. Thank you very much.
Thank you very much, Pasha, for your nice talk. Feel free to ask questions from the audience.
Yeah, I have a question. Thanks a lot for a nice talk. I wonder if you could say a bit more about why we might expect these connections to hold between the Ising model or these other electrical resistant networks that you mentioned briefly at the end, between all these kinds of models and the orthogonal Grassmannian. Like what is it about the structure of the probabilities that mean that we might expect these sorts of connections?
Yeah, that's a good question. And I have no idea. I didn't expect that to be true. And actually, I mean, it's a good question in the sense that there's all these other statistical mechanical models, and you want to know which ones of them give you some other nice things in total positivity. And I have no way of telling if, let's say, percolation or something else is related to total positivity. So we kind of discovered this by accident, and I don't have any systematic way to tell.
Okay, thanks.
Any other questions?
I have a really elementary question. So you have this map from MR, like this boundary correlation matrix, and you do this doubling map, and then you can compute very explicitly that image and understand its Plucker coordinates and so on. So is it really easy to read off entries of the boundary correlation matrix as special Plucker coordinates, or like basically, can you go easily from the Plucker coordinates to the entries of the boundary correlation matrix? I mean, I guess it's an injection, so in theory you can do it. Is it just like a formula?
In practice, there is a formula. I don't know if it's easy, but there is a rational function where you have a bunch of Plucker coordinates on top and a bunch of coordinates on the bottom. It's very explicit. But my favorite way is a little bit different, which is basically you take any. Do I? No. You take any. You have your n by 2n matrix, which you can choose an arbitrary matrix that has the same row span as your original one. So you want to recover the n by the special boundary correlation matrix from this one. And if this matrix is A, then the actual formula here for this matrix is going to be A times K inverse times A, or something like this, and A times K or something, where K is the matrix which has 1/2, 1/2, 1/2, 1/2. So it's a 2n by, let's say 2n by n matrix, which looks like this. And so well, the key point. Yeah, let me just say that basically, if you write down this product, so A times K is going to be X squared n by n matrix. So if you multiply on the left, that means you apply row operations to this matrix here. And I claim that the result is going to have entries which are correlations.
Okay, thank you.
Yeah, thanks.
Thanks. Are there other questions? I might have a question for no other questions. Yeah, okay. Yeah, I wanted to ask, so you can, you chose a special curve gamma theta, and then you computed the span of it inside the orthogonal Grassmannian. I was wondering, yeah, thanks. I was wondering whether what you know about the space carved out inside the orthogonal Grassmannians about these critical models, and whether you have a general characterizations or when you vary theta or for other, not even, yeah, for more in generality, how does it look like this space carved out inside the orthogonal Grassmannian?
Yeah, that's a great question, and I actually have a separate paper on that. So you can
yeah.
Right. So for the Ising model, you can ask what happens if I vary the thetas over all possible, like which thetas are allowed and what happens if you vary them. And more generally, you can generalize this to the critical dimer model and ask the same question. And yeah, I call these the critical varieties in the Grassmannian. And yeah, so you can prove all kinds of nice results about them. So yeah, there's another paper which came out, I think yesterday or today or something like this, about the totally non-negative critical varieties. Yeah, you can study those, and I encourage everyone to try. There's many questions, and I can't really answer most of them. So.
Okay, thanks. Okay, yeah. So I think we can wrap up. And of course, if you have any questions after, we can stay a bit longer. But just to say that we're looking forward to see you next week. Next week, we will have Candy Bothwell from Oxford and talking about recent developments on queens on the torus-shaped chessboard, and it will be organized by Michael Simkin. So I'm looking forward to seeing you there. And thank you for coming again. And we can stay if you have more questions for Pasha and for any discussion if you'd like. Thank you very much.